So as we talked about the other day, a velocity versus time graph shows me how fast and in what direction an object is going at various points in time. Okay, so if I'm looking at this velocity versus time graph, at time 0, how fast was the object going? 0. Okay, because we're down here at the bottom of the graph. At time 0, the velocity was also 0. So what is the object doing between time 0 and time 4 seconds? It's accelerating, right? It's increasing its velocity in a positive direction. Would I be able to calculate its rate of acceleration? Yes, okay? We learned that we can calculate acceleration with this formula. Final velocity minus initial velocity divided by time. The graph tells us all of those things. It tells us our initial velocity was 0. It tells us our final velocity for this section anyway is time 4 seconds. Okay, and 8 meters per second is the final velocity. Okay, so we can plug those numbers in and very quickly have our answer. 8 meters per second was our final. Our initial was 0. That took 4 seconds. 8 divided by 4 is 2 meters per second squared. Remember, that's the units for acceleration. We'll talk more about that when we talk about acceleration, but it's meters per second per second. Meters per second squared is quicker than saying meters per second per second. Okay, all right. Everybody okay with calculating the acceleration? Okay. What's the acceleration between 4 seconds and 10 seconds? It stays at the same speed, right? Is it accelerating at all? No. Can I prove that mathematically? Yeah, I can use this formula to prove that. Okay, instead of using the numbers I had in here before, okay, I'm going to use, all right, at time 4 seconds, my initial velocity is 8. My final velocity is 8. Okay, so if I go 8 minus 8 over 6 seconds, what do I get? 0, because 8 minus 8 is 0. There's no acceleration. Its velocity didn't change. Okay, acceleration is a change in velocity, and the velocity didn't change here. Everybody all right with that? Okay. Now, I think the thing we had the most trouble with was calculating the displacement. Okay, that was that we were doing all the shapes and stuff. Okay, so let's look at that from kind of a different point of view. Okay, in this first section here, where my speed is changing, okay, am I still moving forward? Right? If I'm accelerating, I'm still moving forward, right? My speed is actually getting greater. So I could calculate my displacement by using this formula. V equals d over t. Okay? I could calculate d using that formula. The problem is that my speed is changing. It's not a constant number. Everybody all right with that? Okay. So remember, this formula is actually average velocity divided by, or equals, sorry, displacement divided by time. Okay, so I can take into account that my speed is changing and just use the average. If I go from 0 to 8 over 4 seconds, what's my average speed during that time? I started at 0 and went to 8. Half the time I'd be going faster, half the time I'd be going slower. 4. Okay, my average velocity would be 4, right? For 2 seconds, I was going slower than 4. And for another 2 seconds, I was going faster than 4. So my average would be 4. Everybody okay with that? All right, so here's where we get that. I told you the other day, we could calculate the displacement by finding the area under the line. And what we're doing when we do that is using this formula. We're solving for d, so we're saying average velocity times time. So I bring time over here. Okay, everybody with me there? That I've manipulated that formula. Is everyone okay with that? Okay, so if I want to calculate my average velocity, it is the change in velocity divided by what? By 2, right? We said it was halfway up. Okay, so my average velocity was halfway between my initial and my final. Halfway between 0 and 8 is 4. Okay, so would this be the height of my triangle divided by 2? Okay, that's where this comes from. The time is the base of my triangle. Okay, so I'm going height divided by 2 times base. Okay, whoops, sorry, that says it's supposed to be base. Okay, base times height over 2 is taking the average velocity and multiplying it by time. Okay, I'm just taking into account that the average velocity is halfway up the triangle. Okay, does that make a little more sense than the way I explained it the other day? Okay, all right. If I wanted to calculate the displacement over the whole trip, I'd find this triangle, and then I would find this big rectangle here, right? The velocity doesn't change for this part, so I'm still doing this, average velocity times time. It's a rectangle, so I'm just going to take the base, that's the time, and multiply by the height, which is the average velocity, 8. It doesn't change. Okay? So that's why the shapes work. Okay? We just say calculate the area underneath, because it's the same as finding the average velocity and multiplying by time. Okay? It's just a little bit quicker than doing it that way. Okay. All right. I want you guys, using this graph, okay, to do a couple of things. Okay? The first thing I want you to do is calculate, let's say, calculate the acceleration between 2 and 5 seconds, right? This here is 5 seconds, okay? So acceleration between, okay? Find the acceleration between 2 and 5 seconds. All right, I'll give you a couple minutes on that one. All right, so again, we always calculate acceleration by finding the change in velocity, so VF minus VI, and dividing by time. Okay, we already know the time is between 2 and 5 seconds, so how long is that? 3 seconds. Okay, our final velocity is 10 meters per second according to the graph. And our initial velocity, for this section anyway, according to the graph, is 4 meters per second. So we've got 6 over 3. Our acceleration there is 2 meters per second squared, and that would be positive because it's accelerating, it's going faster. Okay. All right, next thing I want you to calculate. I want you to calculate the displacement between 0 and 7 seconds. Okay, so between 0 and 7 seconds, so we're going to here. Okay. Calculate the displacement between 0 and 7 seconds. Okay, so what's our first step in finding this displacement going to be? Right, draw out the shapes. That's our best bet to start off first. So there's a couple of different ways to do this, but probably the most efficient way is to make a rectangle, okay, that goes all the way across here. Okay, then I would say probably this triangle here, and then this rectangle. Okay, I think that way it's only 3 shapes. You could have made it more shapes if you wanted, but I think that's the most efficient way to do it. Any way you do it, we have to calculate the area underneath the line. Okay, so this rectangle here is going to calculate how far we would go if we just traveled at 4 meters per second all 7 seconds. Okay, and then we're going to add on to that how far we went as a result of accelerating and then traveling at this speed. Okay, that's what those shapes are essentially saying. All right, so this one here is going to be 4 times 7. Okay, everybody with me on that? So this is going to be 28 meters down here. This triangle here, okay, has a base of 3 seconds, and it has a height of 6 meters per second. All right, so 3 times 6 is 18, divided by 2 is 9 meters. And then we have this rectangle here that has a base of 2 seconds and a height of 6 meters per second. Okay, so that'll be 12 meters. Okay, everybody okay with what I did there? All right, what do I do with those 3 numbers? Add them up, right? Okay, so I got 3749. Positive 49 meters, because displacement's vector. Okay, these are all above the x-axis, so that's our displacement to there. All right, if I asked you to calculate the displacement over the whole trip, then you just have to add on this triangle and this rectangle underneath. Okay. All right. Any other questions on how we did that one? Okay. So this one changes things. It goes down into the negative. It doesn't really change what we have to do. It's just some of our answers will now be negative. All right. So first thing I want you to calculate. I want you to calculate the acceleration, okay, between 2 and 7 seconds. Here. Okay, so we have, okay, again, the formula we always use to calculate acceleration, change in velocity, VF minus VI, over time. Okay, our final velocity in this case is -6. Okay, and our initial velocity is +4. Okay, and then our time is between 2 and 7 seconds, so that's 5 seconds. All right, so we've got -6 minus 4 is going to be -10 divided by 5, and our acceleration will be -2 meters per second squared. Is it okay for that to be negative? It is. We were accelerating backwards. Okay, it would be equivalent to, and I think I've used this example before with you guys, but if I had a bungee cord across and I ran into the bungee cord, I'd be moving forward to start with, but as soon as I hit the bungee cord, I'm going to start slowing down. When I'm slowing down, I'm actually accelerating backwards. Okay, I can actually move forwards while accelerating backwards. I'm just going to slow down, eventually stop, and then start actually moving backwards and accelerating that way as well. Okay, it's no different than when you throw something up in the air. Okay, as soon as this marker leaves my hand, which way is it accelerating? It's accelerating upwards when it's in my hand because I'm pushing it. But as soon as I let it go, it starts to slow down because what's grabbing it? Gravity, right? So it's even though it's moving up, it's accelerating downwards. That's why it stops. If it accelerated upwards, I could put it into orbit by throwing it, which is not possible. I mean, I'm huge, but I'm not going to be able to throw it into orbit from here. Okay, and I'm not huge. Okay, let's see if we can get here total displacement. Okay, I want to calculate the total displacement over the whole trip. Okay, so that's your next challenge. All right, so I've got part of the time where the object's moving forwards and part of the time where the object's moving backwards. Okay, from the looks of it, it spends more time going backwards than it does going forward. So most likely, this is going to end up as a what kind of number? Negative number. Okay, good. So we've got, okay, this first shape here that we'll need to calculate, and then this triangle, and then this triangle here, and then followed by this rectangle here. All right, so this rectangle here is 2 on the bottom and 4 high, so it's +8 meters. All right, this one will be +4 meters because it's 2 by 4 but divided by 2. All right, then this one here is 3 seconds long on the base and -6 high, so it's going to be -9 meters. And then this is 3 seconds, okay, so it'll be -18 meters. All right, so we've got 12 positive and we've got 27 negative. All right, so our total here is -15 meters for our total displacement. Okay, is that making a little more sense now? Are we feeling a little more comfortable with those? Because I'll be honest with you, Luke, I put one just like this on last year's unit exam. Okay, so expect that you're going to get a question just like this on your unit exam, on your quizzes, okay, things like that. You're going to be expected to be able to do a calculation just like this. The question was calculate the acceleration during the part where there was accelerating, and the second part of the question was calculate the total displacement. All right, so I'm not going to ask you anything different, okay, this year, just be a slightly different graph, but that's the kind of thing you're going to be asked. Okay. All right, so actually there's a graph here that was on the sheet that I want you guys to go back to. And it's this one. Okay, I know it's kind of blurry, but here it's 0, 100, 200, 300, 400, and 500. Okay, and then this is 250, 500, and 750. Okay, just so you know what the lettering on there is. All right, so it's a position versus time graph. Okay, so this is in meters now on the y-axis. This is in seconds here on the x-axis. So position versus time graph. Okay, see if you can calculate the things it asks for. All right, so it's a position versus time graph. We don't do things the same way we've been doing on the velocity versus time graphs because it shows us different information. This graph shows us where the object is at various points in time. Okay, so if I want to calculate the average speed over the whole trip, average speed is total distance divided by total time. Okay, we already know the total time is 500 seconds. The total distance is how far it went over the whole trip. So over the course of this trip, it went from 0 to 750 meters, and then from 750 meters back to 0. Okay, so how far did it go? 1,500 meters. Remember, how far? Distance doesn't care whether you went forward or backward. Just cares how far. Went 750 forward. In the first 200 seconds, it went from 0 to 750. Okay, then it was stopped for a little while here in section C, and then it went from 750 back to 0 from 300 to 500 seconds. So our total distance, is 1,500 meters. Okay, divided by 500 seconds. Well, we're looking at 3 meters per second as our average speed over the whole trip. Okay. Didn't need to draw any shapes here because it's a different kind of graph. It already told me how to get the distances. I didn't have to go like really out looking for them. Right? Okay, so if I want to calculate average velocity, okay, here in part B, remember average velocity is the total displacement, okay, over the total time. Okay, now it's just asking for that one section, but this is still true. Right? So give that one a try. Between 300 and 500 seconds, what is the average velocity? Okay. All right, so for part B, average velocity between 300 and 500 seconds. So at 300 seconds, we're at a position of 750. At 500 seconds, we're at a position of 0. What's my displacement? Negative 750. Okay, guys, here's the other formula that's on your formula sheet. Displacement is final position minus initial position. I may have ended up at 0, but my displacement between here and here is negative 750 because I started at 750 and ended at 0. I walked backwards 750 meters. Okay, you guys follow me there? The total displacement over the whole trip is 0 because I started at a position of 0 and ended at a position of 0. But for this part, okay, it's 0 minus 750. And then I divide that by the 200 seconds worth of time. There's my total displacement divided by my total time. Right? When I do that, I should get 3.75 meters per second. All right, total displacement we already talked about. Okay, the distance traveled in the first 200 seconds. Well, I went from 0 to 750. How far did I go? 750 meters. Okay. All right, we're still going to spend a little bit of time practicing this, but as long as we're kind of getting a grip on it, okay, that's the big thing. Now, when you get a graphing question on a test, this is the key thing. You have to make a note of what type of graph you're looking at. Because as we've seen, you calculate things differently depending on what graph you're dealing with. And the most common mistake I see is people solving for something on a velocity versus time graph as though it's a position time graph. And that won't get them the right answer, and vice versa. Okay, so we have to make sure we know, all right, this is a velocity versus time graph. I got to do things differently than if it was a position time graph. Okay, because there's nothing worse when I'm marking it than to look at it and go, oh, that person so knew what to do but didn't make a note of what kind of graph it was. Okay, and so they use all the wrong method for that graph. Okay, alrighty. So a couple of reminders here, guys. That graphing lab, okay, that we did this week, okay, that's due next week. So make sure you're getting a heads up on that, and if you need some help with it, that you're coming in next week during scheduled help. Okay, it's due on Wednesday, so come see me Monday or Tuesday if you want me to go over it with you and just have a look at a few things. Okay, make sure that you're taking advantage of that. Okay, we're about a third of the way through the unit, so probably next week I will tell you about when our unit exam will be. Okay, I'm looking at like very beginning of June, possibly very end of May, probably somewhere in there. Okay? It doesn't take long for the year to get away from you. Okay? Our last unit, it takes no time at all. Like we're done that in, well, I've taught it in as many as 5 days. Well, as few as 5 days, as many as 12. So we'll see what kind of time we have for that. It's one I can rush through. But know that this unit will be coming to an end, very end of May, beginning of June, somewhere in there. Okay. All right. So you got a few minutes here. I would say, you take out your phones and work on your lab a little bit, okay? Or I might even have the Chromebooks in here. I'll have a look.